Good day, everyone. My name is Owen Diesenhaus, and I would like to thank the judges for the opportunity to present my work in the poster session. I attend the Potomac School, and my paper is titled Molecular Dynamic Study of Ionic Liquid Electrolytes with Organic Solvent Additives for Aluminum-Ion Batteries. As written in the abstract and introduction, climate change and energy production and storage are the most pressing global issues facing my generation. With a focus on energy storage, my project investigates the characterization of aluminum-ion batteries, or AIBs. More specifically, I investigated the effect of different organic solvents on the ionic liquid electrolytes using molecular dynamics simulations. To complete a molecular dynamics simulation, I started by modeling the components of the simulation, which were the four components in the left of Figure 2. I then input these components into a program that placed them into boxes, which represented the virtual space where the components would be free-floating at the beginning of the experiment. Figure 3 shows a close-up of one of these boxes, with each component a different color. I made three kinds of boxes, ones using only aluminum trichloride and EMI-MCl, which represents the control as the components are typically used as base electrolytes, ones with the addition of toluene, and finally ones with the addition of dichloromethane, or DCM. For each type of box, I made one acidic system and one neutral system based on Lewis acidity. MD simulations were then run in each system and were analyzed using graphs of electrostatic interaction energies and radial distribution functions, or RDFs, and their integrals. What you see in Figure 4 is the output box obtained after running the simulation. Figure 5 represents the electrostatic interaction energies between aluminum trichloride and EMI-MCl, which had a consistent value for both of the no-solvent systems of negative 3,000 kilocalories per mole, indicated by the dark blue line. In comparison, the neutral systems with organic solvents show a decrease, and the acidic systems show an increase in this value. This is an important finding because acidic systems are used in physical AIB electrolytes, and the increase would lead to greater solubility of the aluminum trichloride in the EMI-MCl, and therefore would improve the electrolyte's ability to store energy. Figures 6 and 7 give additional insight into the complexes that form within AIBs by showing the average distances of the solvated molecules. Figure 6 shows the neutral systems, while Figure 7 shows the acidic systems. In each figure, the graph on the left examines the solvation of negative chlorine ions around positive EMIM ions, and the graph on the right examines the solvation of chlorine ions around an aluminum trichloride center. The peaks in the graph, like this one, denote the distance of the first solvation shells for each pairing. From these graphs, it was determined that the solvation shell around EMIM is located 4.3 angstroms away and 4.1 angstroms away around the aluminum trichloride centers. Taking the integrals of these RDFs, I then determine the average number of coordinated molecules and ions for both of these complexes. The numbers in the tables correspond to the value of the graphs at the first solvation shell given by the previous RDFs. The integral values varied depending on the acidity of the system and the inclusion of solvents. To better show the effect of the acidity and solvents on the integral and confirm my other conclusions, I would do more simulations using gradually increasing acidity and varying concentrations of solvents. I would like to thank the JSHS organization and the judges for choosing my submission and allowing me to present my work. My mentors, Dr. Trant, Dr. Timori, and Dr. Kozar from the University of Windsor for guiding me in this work, and the science teachers and administrators at the Potomac School. Thank you.